For a long time, Titan was treated like a curiosity. Big moon, thick haze, lots of chemistry, but nothing that suggested real surprises were waiting underneath. When NASA's Cassini spacecraft began flying past it in the mid-2000s, the goal was mostly confirmation. Measure the atmosphere, map the surface, fill in the blanks. Then the data started to feel off. Signals coming back from Titan didn't behave the way they should for a frozen, inactive world. Gravity measurements hinted that the interior wasn't as rigid as expected. Radar scans showed surface features that looked oddly familiar, like landscapes shaped by movement, not just impact scars and erosion. Even the atmosphere refused to act like a static blanket. It was changing, cycling, doing things that suggested an energy source nobody had planned for. At first, these were treated as small anomalies. Instruments drift, models get things wrong. But the anomalies kept lining up, pass after pass. Titan wasn't just chemically interesting, it was doing something. By the time scientists realized what they were looking at, the idea of Titan as a quiet, frozen moon was already gone. In its place was a world that didn't fit neatly into any category NASA had prepared for. Not a dead rock, not a simple ice ball, something in between, and possibly something entirely new. That moment when expectation broke is where Titan stopped being just Saturn's largest moon and started becoming one of the most unsettling places in the solar system. Before Cassini ever arrived, Titan already felt figured out. Scientists knew it was cold, extremely cold, around minus 290 degrees Fahrenheit at the surface. They knew it had a thick atmosphere made mostly of nitrogen with methane mixed in. That alone made it interesting, but not threatening to existing ideas. The assumption was straightforward. Titan was a frozen relic from the early solar system. Whatever heat it once had was long gone. Any internal activity should have shut down billions of years ago. Beneath the surface, models showed solid ice all the way down. No movement, no surprises. Even the atmosphere was expected to be passive. Sunlight breaks methane apart. The methane disappears. Over time, it should fade away unless something replaces it. Most researchers assumed Titan was simply running out the clock, slowly losing what little complexity it had left. The surface fit that story too. Early telescope images showed nothing dramatic, just a smooth orange blur. No mountains reshaped by tectonics. No signs of volcanism. No reason to think the interior was still doing anything at all. In other words, Titan was expected to be chemically interesting, but physically boring. A world good for studying prebiotic chemistry, but not a place where anything active was happening now. That expectation shaped everything. The instruments, the mission goals, the questions scientists thought were worth asking. Cassini wasn't sent to look for internal oceans or active geology on Titan because nobody seriously thought they were there. That assumption didn't survive contact with real data. The shift happened slowly, then all at once. Cassini's gravity measurements were the first real crack in the story. As the spacecraft flew past Titan, its speed changed in subtle ways. Those changes revealed how mass was distributed inside the moon. What scientists saw didn't match a fully solid interior. Titan was flexing. Not much, but enough to matter. That kind of flexibility means one thing. Something beneath the ice wasn't frozen solid. Then came the radar data. Cassini's radar could see through Titan's thick haze and map the surface in detail. Instead of a uniformly ancient landscape, it found regions that looked geologically young. Smooth plains with few impact craters. Features that suggested resurfacing had happened recently, not billions of years ago. The biggest surprise followed soon after. Methane. Titan's atmosphere was still rich in it, even though sunlight should destroy methane relatively quickly. On a geological timescale, it should have vanished. Yet it was clearly being replenished. That meant there was an active source somewhere. Piece by piece, the picture changed. Titan likely had a global ocean beneath its icy shell. Not liquid water like Earth's oceans, but water mixed with ammonia, kept warm by internal heat. That ocean could interact with the surface, feeding methane into the atmosphere through cracks or icy volcanism. This wasn't a minor adjustment to the model, it was a complete rewrite. Titan wasn't a frozen leftover. It was an active world with energy, motion, and ongoing chemical exchange between its interior, surface, and atmosphere. NASA didn't set out to find that, but once the evidence lined up, there was no way to ignore it. Once scientists accepted that Titan was active, the comparisons became impossible to ignore. Titan has weather. Real weather. Clouds form, rain falls, rivers carve channels into the surface. Lakes and seas collect in lowlands near the poles. The difference is that none of this involves water. At Titan's temperatures, water is rock. Methane and ethane take its place. That creates a cycle that feels eerily familiar. Methane evaporates into the atmosphere. It condenses into clouds. It rains back down, flows across the surface, and gathers in lakes. Over time, it returns to the atmosphere again. A hydrological cycle built from hydrocarbons instead of H2O. Even erosion behaves in recognizable ways. Cassini images showed river networks branching like those on Earth. Shorelines that rise and fall with seasonal changes. Deltas forming where liquid empties into larger bodies. These are processes we associate with a living planet, not a frozen moon nearly 1 billion miles from the sun. Beneath all of that, the subsurface ocean ties everything together. Heat from the interior drives slow motion in the ice shell above it. That motion may open pathways for material to move upward, linking the deep ocean to the surface and atmosphere. On Earth, that kind of connection is critical for chemistry to grow complex. Titan mirrors Earth's structure in a distorted way. Solid crust on top, a global ocean below, active cycles exchanging material between layers. But every ingredient is wrong. The temperatures are brutal. The liquids are hydrocarbons. The chemistry follows rules we barely test in laboratories. It feels familiar enough to recognize and alien enough to force new thinking. That combination is what makes Titan so dangerous to assumptions. Titan forced a quiet but serious rethink of where complexity can exist. For a long time, habitability was tied to a narrow idea. Liquid water on the surface, moderate temperatures, sunlight as the main energy source. Titan violates almost all of that. And yet, it keeps checking boxes scientists didn't expect to see filled so far from the sun. The subsurface ocean alone is enough to change the conversation. A global body of liquid water in contact with rock, warmed by internal heat and chemically connected to the surface. On Earth, that combination is powerful. It drives reactions that build complexity over time. Titan shows that you don't need Earth-like conditions for those ingredients to come together. Then there's the chemistry. Titan's atmosphere is a factory for organic molecules. Sunlight breaks apart methane and nitrogen, then recombines them into more complex compounds. Some of those compounds fall to the surface. Others may sink through cracks in the ice. Over long timescales, that creates a steady flow of raw material moving between environments. What makes this unsettling is that Titan isn't a rare exception. If a moon this cold and distant can stay active for billions of years, then similar worlds could exist all over the solar system and beyond. Places that don't look friendly at first glance but quietly maintain energy, motion, and chemistry beneath the surface. Titan didn't just expand the list of interesting places, it expanded the definition of what an interesting place even is. It showed that life-relevant processes don't need comfort, they need persistence. And Titan has that in abundance. Titan started out as a control case, a moon that was supposed to confirm what scientists already believed about cold, distant worlds. Instead, it did the opposite. It showed that even far from the sun, even locked in deep freeze, a world can stay active, connected, and chemically alive. Nothing about Titan looks welcoming. The surface is hostile. The temperatures are extreme. The liquids would be deadly to us, but step back far enough and the structure feels familiar. Layers that talk to each other. Energy moving slowly but steadily. Chemistry that never quite shuts down. That's the real surprise NASA didn't expect to find. Not just lakes of methane or a hidden ocean, but a system that refuses to go quiet. Titan doesn't care about our definitions. It doesn't need to resemble Earth to behave like a world that's still evolving. As new missions prepare to return there, the question isn't whether Titan is strange. It's how many other places like it we've already overlooked.